Have you ever wanted to predict the future? To look at the total chaos of stock prices, weather patterns, or sales figures and just see a glimpse of what's coming next? Well, that's not magic, it's the science of time series analysis. So let's begin our quest to understand the past so we can actually forecast the future.
Our journey is going to be broken down into 5 key stages. First, we'll learn to read our map, the data itself. Then, we're going to put on our detective hats and deconstruct all the hidden patterns. After that, we'll uncover the one golden rule of forecasting, meet 2 pretty fascinating characters called ideal randomness and the drunkard's walk. And we'll finish on a question that perfectly sets us up for our next adventure.
All right, first things first. We absolutely need to understand what kind of data we're dealing with here, because not all data is created equal. And in our world, timing is everything.
So let's start with a really key distinction. You have cross-sectional data, which is kind of like a snapshot, a survey of different households at one single moment in time. You could shuffle the order of those households, and it wouldn't change a thing. But with time series data, the order is the story. Yesterday's stock price has a direct impact on today's, which will then influence tomorrow's. See? The sequence is everything.
A great way to think of it is like this. The data we have isn't just a collection of random scenes from a movie. No, it's the one and only version of the movie that was actually filmed in order. Our job is to watch it carefully enough to make a really good guess about how the very next scene is going to play out. Okay, so now that we know what our data looks like, it is time to put on our detective hats. A time series is rarely just one simple thing. It's usually a combination of several different patterns, all layered on top of each other. The first and, let's be honest, most obvious clue is the trend. Is the data generally moving up, down, or is it staying flat over a long period? Think of a company's growing annual profits, or maybe the slow decline in a city's population. That's the trend. It's the big picture direction. Next up, we've got seasonality. These are those predictable ups and downs that happen like clockwork. Retail sales spiking every single December for the holidays, or energy usage peaking in the summer and winter. If a pattern repeats over a fixed, known time frame, like a day, a week, or a year, yep, that's seasonality.
Now this brings us to a trickier concept: cyclical patterns. Just like seasonality, these are waves of ups and downs. But, and this is the key, they don't have a fixed period. Think of things like business cycles, those periods of economic expansion and recession. We know they happen, but you can't just mark your calendar for the next one. They're much longer term and way less predictable.
And finally, what's left over after we account for the trend, the seasonality, and the cycles? Well, that's the irregular component, or what we often call noise. It's the random, unpredictable stuff, a sudden market crash, a natural disaster. The things that just don't follow any pattern at all.
Okay, all of this, it all builds up to the most important concept in our entire quest. If we want to build models that can actually forecast the future, our data needs to follow one golden rule. This, right here, is the secret that unlocks reliable predictions. And that really brings us to the core problem, doesn't it? We just talked about how data has trends and seasons, it's constantly moving. So how in the world can we build a model on something whose fundamental behavior is always changing?
The answer is a concept called stationarity. Think of it like a river. A non-stationary river might be flooding one year and just a dry bed the next. Its average level is all over the place. But a stationary river, it always flows around the same average level. Sure, it might have ripples and waves, but the fundamental nature of that river stays consistent. That's a stationary series. It's predictable precisely because its underlying rules aren't changing on you.
So why is this our golden rule? Well, because so many powerful forecasting tools are specifically designed to work only with stationary data. If you try to feed them non-stationary data, you can get what analysts call spurious results. I'm talking predictions that look good on the surface but are completely meaningless. It's like finding a connection between ice cream sales and shark attacks. By making sure our data is stationary first, we make it so much easier to model and get far, far more accurate predictions.
Okay, with our golden rule established, let's meet our first key character in this world of stationary processes. This is the absolute purest form of randomness, the baseline that we measure everything else against.
Meet white noise. It's perfectly stationary. Its average is 0, its variance is constant, and, this is crucial, it has no memory. Today's value tells you absolutely nothing about what tomorrow's value will be. It's completely, utterly unpredictable. And because of this, it serves as the fundamental building block for pretty much all other time series models.
And here's the practical magic of white noise. When you build a forecasting model, you always look at the errors. You know, the difference between your predictions and the actual values. If those errors look like white noise, that is a huge sign of success. It means your model has squeezed out every last ounce of predictable information, and all that's left behind is pure, unforecastable randomness. You've done your job.
But not all randomness is created equal. Let's meet our second character, a process that can totally fool you into thinking there's a pattern, when in fact, it's just a memory-filled stroll and a total unpredictability.
This is the random walk. And honestly, the analogy is perfect. Just imagine someone taking steps in totally random directions. Their next position depends entirely on where they were a moment ago, plus a new random stagger. It might look like they're actually heading somewhere, but really, it's just an illusion created by a whole series of random choices.
The process itself is incredibly simple. You just start somewhere. Your next position is just your last position plus a little random nudge of white noise. That's literally it. But this simple formula creates a series that looks like it has trends and momentum when it's all just the lingering effect of past random shocks.
And this is the crucial takeaway. The random walk is not stationary. It completely breaks our golden rule. Because each random step adds more and more uncertainty, its potential to just wander off in any direction grows over time. Its behavior isn't consistent, which makes it incredibly difficult to forecast directly.
So this brings our initial quest to a close with one massive question. We know stationarity is the key to prediction, but we also know that a lot of real-world stuff, like stock prices, behaves a lot like a non-stationary random walk. So how do we bridge that gap? How can we possibly tame this messy, unpredictable data and make it follow the rules? Well, that's the challenge, and that is a story for our next explainer.